Now we are going to analyze the welded joint with eccentrically loaded condition. And here you have the plate here, and the plates are joined by using the welding joint shown here, and the load is acting a distance from the center of gravity or centroid of welding. So the centroid of the welding is represented by the point O here, and the force is acting here, and it is actually this is an example of eccentrically loaded welded joint, eccentrically loaded welded joint. So for the analysis, initially we will transfer the force from the present line of action to the centroid of the welded joint. So while you are transferring a force from one point to another, you will have a force and you will have another moment. And the force passing through the centroid will be equal to the same magnitude F in the same direction, and the moment will be equal to it will be clockwise direction in this case with respect to the centroid, and the magnitude of the moment will be equal to force into the distance, shorter distance from the centroid to the force, like a line of action. So then we will consider both these cases one by one. Initially, we will consider the force acting through the centroid, and the magnitude of the force is equal to F itself. So the welding here will experiencing a shear stress, and the magnitude of the shear stress will be equal to the force divided by the area. The shear force V here will be equal to the F in this condition. So that we can call it as a primary shear stress. So the primary shear stress will be equal to the force divided by the total area of the weld. And next we will consider the moment. Moment is acting clockwise in this condition, and you have a magnitude of moment that will be equal to the force into the distance from centroid to the line of action of the force. And we represented that moment by using the letter M, capital M here. And if you look at any point in the weld that located R distance of R from the centroid, then you are able to find out the shear stress, secondary shear stress due to the moment will be equal to the moment into the distance from the weld centroid to the point under consideration divided by the J. J represent the polar moment of inertia of the entire weld region. And here, then you can find out two shear stresses. One is the primary shear stress because of the shear force, and you have secondary shear stress because of the moment. So you can find out the total shear stress by using the vector addition of the forces caused by the shear stress, primary shear stress and secondary shear stress. From that one, you are able to find out the force and total stress. Then by using that one, you can find out the size of the weld. So the challenge for solving that problem, initially you need to find out the area of the weld. The area of the weld is the area of the throat section where you have the minimum area, where you will have the maximum shear stress. So the area which you are able to find out by using the throat area. So we are considering a horizontal weld region, and you have a vertical weld region. This vertical weld region have the width is equal to B, and the length of the weld is equal to D. And in this condition, horizontal weld region have a depth is equal to D, the weld throat section is equal to D, and the length of the weld is equal to B2. So then this B actually represents the throat area, and if H1 represents the leg size of this vertical weld, then the throat will be equal to B1 will be equal to 0.707 H1. That means H1 into cos 45. So similarly, in this condition, D2 represents the throat of the weld, the horizontal weld. And in this condition, suppose H2 is the weld size, leg size, then you are able to find out D2 is equal to H2 into cos 45. That is equal to 0.707 into H2. H1 and H2 represent the respective weld size of this vertical and horizontal weld. Then the area you are able to find out at the throat section will be equal to this area, B1 into D1 plus B2 into D2. So this represents the total area of the weld at the throat section. Now the next thing, we need to find out the polar moment of inertia of the weld with respect to the centroid of the weld. And here centroid of the weld represented by G. We have this horizontal weld and you have the vertical weld. So the centroid is represented by using this. Centroid is represented by using the capital letter G that actually represents the centroid of these two areas. And G1 represents the centroid of this vertical weld, will be represented by weld 1, and G2 represents the weld 2, that is a horizontal weld. So initially we will consider the weld 1, the area, vertical area. If we look at let's say we have the x-axis represented by this one, and y-axis represented by here, the local y-axis and x-axis. So if we want to find out the moment of inertia about x-axis and y-axis, then Ix will be equal to B1 into D1 cube by 12. That is the standard equation. And Iy is equal to D1 into B cube divided by 12. And that is the standard equation. So once you find out Ix and Iy, the moment of inertia about polar moment of inertia about z-axis, that is perpendicular to the screen, which you are able to find out by addition of Ix plus Iy. So the moment of inertia of the weld one, that means the vertical weld with respect to its centroid, that centroid of that weld will be equal to Ix plus Iy, that is equal to B1 D1 cube divided by 12 plus D1 V1 cube divided by 12. So similarly for this horizontal weld, you are able to find out the moment of inertia about its centroid G2 is equal to Ix plus Iy, that is equal to B2 D2 cube divided by 12 plus D2 B2 cube divided by 12. Now, if we want to find out the center of gravity G of the total weld with respect to G1 and G2, you are able to find out using the standard equation which you have studied, x bar of the centroid, x coordinate of the centroid of the weld. You are able to use this equation A1 x1 plus A2 x2 divided by A. The y coordinate of centroid G is equal to A1 y1 plus A2 y2 divided by A. So x1 represents the centroid of this weld 1, x coordinate of the centroid of the weld 1, and x2 represent the x coordinate of centroid of weld 2, and y1 and y2 represent the y coordinate of weld 1 and y coordinate weld 2. So from here you are able to find out x bar and y bar that represent the centroid of the total weld area. So once you find out this one, you are able to find out the distance. It's the distance of the centroid of G1 and G, that you are able to find out by using this equation. R1 will be equal to x bar divided by x1 whole square plus y bar by x, since x-axis passing through this centroid. And similarly, you are able to find out the distance from G2 to G by using this equation, y2 minus y bar whole square plus x2 minus x bar whole square, the root of whole root of. So if you find out this one, you have the polar moment of inertia of this weld 1 and weld 2 with respect to its centroid. So if you want to find out the centroid with respect to the total weld area, then you have to use the parallaxis theorem. So then you can find out by using J is equal to Jg1 plus A1 into R1 square, AD square. That is a normal standard convention which we use to when we use the parallax theorem. So here R1 represents the distance from these two centroid, and R2 represents the distance from these two centroid. A1 and A2 represent the area of the weld 1 and weld 2 respectively. So from here you are able to find out the total polar moment of inertia of the total weld area. So suppose if the weld size, if we need to find out, initially we can, while solving the problem, initially we can assume some weld size and we can find out the shear stress and check whether it is within the limit or not. If it is exceed the allowable shear stress, then you can assume a higher weld size and repeat the process. That is how you can solve the problem. Now we have another approach. Actually, we can consider these two welds. This, you have this vertical weld and you have this horizontal weld. These two welds you can consider as a line weld. So what is the purpose of that one? So you look at, if you look at here, the B1 of the vertical weld is much smaller than the D1. So when you take this sum, B1 into D1 cube divided by 12 plus D1 into B1 cube divided by 12. So in this condition, the B1 is much smaller than the D1. So B1 cube will be much smaller than the D1 cube. So in this condition, if you look at these two terms, this term D1 into B1 cube divided by 12 will be much smaller compared to the B1 D1 cube divided by 12. So for practical purpose, we will assume that this is the JG1 is only this term, consists of only this term. This term we will neglect. So what is the advantage of that one? This is the moment of inertia about this vertical centroid. So B1 D1 cube divided by 12. And that is the total moment of inertia about of this vertical weld or weld 1 with respect to its centroid. Then you are able to find out for unit broad section, unit width of the broad section, you are able to find out divided by B1. Then D1 cube divided by 12, you can represent the moment of inertia with respect to its centroid per unit width of the rod. So that means Jg1 is equal to D1 cube by 12. If you can consider that per unit width of the rod. So if you want to find out the total for a width of V1, then you have to multiply it by using this one. So that is a concept which we use to consider the weld, treating the weld as a line actually. So then you will find out the moment of inertia of this one and moment of inertia of this one per unit width of the weld region. Unit width means actually the unit width of the throat section. So depending on that one, you are able to, from here, you are able to find out the area, the centroid, and the polar moment of inertia per unit width of the things. So if you multiplied all of this by using the width B1, then you are going to get this is the dimension representing here. Then if you multiply it with this, the throat section, you are going to get the total moment of inertia. So moment of inertia specified here actually the polar moment of inertia per unit width of the throat. So if you want to get the actual moment of inertia for this welding section, you have to multiply it by using the throat section width. That is equal to h into h is a weld size into cos 45. And similar, so like this, if you look at the data book, so if the area, the location of the centroid, and the polar moment of inertia per unit width of the things, which polar moment of inertia per unit width of the throat section, which will be available in the data book. From that one, you are able to use directly for your calculation purpose. And if you multiply it with this unit polar moment of inertia by using the throat section width, you are going to get the throat section of the corresponding things. So you will see this one. You can see it is in the you can see this one in your data book. And also if you want, I can derive one of this one and post it in the group. So we will do some more problems about this one, and I will solve the problems, and I will upload the scan copy in the things. You can refer it. So this idea will be clear when you solve the problems on it. Okay, thank you.